Hello. Um, a transfer orbit now we're talking about, and they start us off by giving us a clue as to the total energy of the transfer orbit because it's not a circular orbit. So we work out the average radius, the average of 3,600 and 8,300, and that's 5,950 kilometers. I'm going to be using GMM an awful lot, so I'm going to just calculate that now, and that will save a bit of time later on. Times 150 times the mass of the planet, so that's 8 times 10 to the 16. Now the total energy here is my GMM, 8 times 10 to the 16, divided by twice the transfer orbit radius, 5,950 times 10 to the 3. So let's work that out. That gives us 6.7 gigajoules. That 6.7 gigajoules is the total energy for these two. The total energy, which is the gravitational plus the kinetic. And what else do we have that's the same? Well, in fact, these 2 points here are at the same radius, so the gravitational potential is the same. It doesn't matter that the spacecraft is sped up, it's still at the same place, so its gravitational potential energy is the same. And these two as well. So we can save a bit of time, and it's basically trying to figure out what's going on. Also, we can use the relationship, which is that the kinetic energy for a circular orbit is minus a half of the gravitational potential energy. So let's go ahead and work this first gravitational potential energy out. That's simply GMM, 8 times 10 to the 16, divided by the lower radius, which is 3,600 times 10 to the 3. 8 times 10 to the 16, which is 22.2, and therefore that one is also 22.2 gigajoules. Now we might as well do the other gravitational potential energy. That's going to be divided by 8,300 times 10 to the 3. So 8 times 10 to the 16 divided by 8,300, and that gives me 9.6 gigajoules for both of those. As I said earlier, they're at the same radius. To get the kinetic energy here, I'm going to work out, well, it's going to be the total energy, which I should have said is negative actually, and in fact these gravitationals are negative as well, otherwise it won't mark it correctly. Let's get precise here. That's going to be the total energy minus the gravitational potential energy. So I'm going to do minus 6.7, and it's a minus, so it's going to be a plus 22.2. That's going to give me 15.5. Same thing for the other one, for this part here. That's going to be minus 9.6. Sorry, minus 6.7, the total energy, plus 9.6, which is 2.9. And using the relationship that I mentioned earlier here, it's a half to go from the gravitational to the kinetic for circular orbits only, not for elliptical orbits. So that's simply 11.1. And this one is 11.12. And now you should see that the burn is needed because there is an increase in kinetic energy at both of these points here. Calculating the impulse is a little bit tricky. If I write kinetic energy in terms of momentum, that might help. So the impulse can be expressed as the square root of 2 times the mass times the kinetic energy. And that's what I need to find the difference for each of these. So for the first one, it's going to be, I'll go back to purple, I suppose. It's going to be square root of 2 times the mass of the space probe, 150, times the kinetic energy, which was 15.5 times 10 to the 9. And I'm going to take away the square root of 2 times 150 times 11.1 times 10 to the 9. So plugging that all in into my calculator. Takes a while, sorry about that. 2 times 150 times 11.1 times 10 to the 9. And yeah, that should give me, so that gives me 332,000 Newton seconds. And I do something similar for the other impulse. It's the same equation. So this time it's the square root of 2 times 150 times the other two kinetic energies. So it's 11.1 times 10 to the 9 and 2 times 150 times 2.9 times 10 to the 9. And that gives me 892,000.